Bismillah. Good afternoon, everyone. Today our lecture will talk about direct and indirect bandgap semiconductor. At first, I want to introduce myself. I'm Ali Alşemeri, student in Muğla University, Kocaman University. I will start by explaining the most important thing, talking about the direct bandgap semiconductor. Now, like I said before, we have two kinds of bandgap semiconductor, direct and indirect semiconductor. We will know why we have these two kinds, what the important difference between these two kinds. Let's talk about from the direct, like this figure below. This will be most important thing to us to understand all this information clearly. If the top of the valence band, at first this valence band, the top of the valence band, I mean this point, okay? And the bottom of the conduction band. The bottom, at first, conduction band, this field is called the conduction band. The bottom of this field, this curve, this point, I mean this point. If this point, the bottom of the conduction band be directly under the point at the top of the valence band, that means this situation is the direct bandgap semiconductor. Why? Because this point directly under this point. That's it. This is the important information about this diagram. Now let's talk about the other. Exist at the same point on the energy versus K. Here, this point, energy versus K. Okay? Because we will use the same line, the energy versus K at the indirect bandgap, and this line will be important to us. This figure below to the germanium arsenide here. Now let's talk about this radiation. This radiation explained to us, showed to us the energy of the energy bandgap, and what that's mean. This energy, this equal HV, that's mean equal the energy bandgap, and at the same time the energy bandgap has another result. This result equal EC, that's mean the energy conduction band here at this field minus the valence energy band here from this field. That's mean EG equal EC minus EV. That's it, shortly. Okay. Now let's go to talk about the second kind of bandgap semiconductor. This is the indirect. Now let's know and explain why we called to the situation indirect. What the difference? Here, this diagram is different and sure important to us to can understand the main importance in this field. If the top of the valence band, like I say, the top of the valence band is point, and the bottom of the conduction band here, the situation here is different. Here, the bottom, this curve here, not like the curve before. The last curve was drawn like this. But here, take another place, take another directions. Let's complete the definition. If the top of the valence band and the bottom of the conduction band, like I say, the bottom of the conduction band, I mean this point, at a different value in the energy versus K diagram. This, the energy versus diagram or line. Here, the situation is different from direct bandgap, because here the bottom of the conduction energy band, the bottom of the can say the bottom of the conduction band directly under another point. That's right, at the same K, the first is K, but at another point, at another direction, not at the same point. Like we say, this diagram is very clear. And if we do some link or connect between these 2 points, the most 2 points to us, this we will see these lines here to do this connect. Now let's talk about the nature of the band gap and what the nature of the band gap, what can do to us, what can, if we do it, what we can know, what we can determine. Now let's talk about that. The nature of the band gap of the semiconductor determines the optical properties of the semiconductors. Optical properties. Let's put these two words underline. That means the band gap is very important to us because will depend on the optical properties. And we have 2 important things. We can determine these 2 points from the nature of the band gap. The first thing is the absorption of light, and the second thing is the emission light in the semiconductor, absorption and emission. All these 2 points, we can determine it by use or know the nature of the band gap. Non-radiation recombination, let's take a look about on this note. The electrons in the silicon is important to us, and I will focus on it because it's cheap and we have this kind in our nature. And in the same time, we can say it's not expensive and very effective at the solar cell field. Okay, silicon don't emit any light when returned to the valence band. The electrons in the silicon don't emit any light when come back to the valence band. Let's answer this question. The questions say what happened to the energy difference between EC and EV. We know energy band gap equal EC minus EV, I mean the valence energy band. What happened to the energy here? This energy difference, I mean sure energy band gap, is emitted. What by emitted this result, what will happen? The temperature to semiconductor will increase and the electrons return back to the valence band. From where? Sure, from the conduction band, will come back to the valence band when the temperature will increase. Okay, this is important. Now, I take all this information from the source, the solid state electronic devices source. But in my researching, I take another important information from another source. The source is photovoltaic to Stephen Cole. Now let's take a look about the source photovoltaic to Stephen Cole. I think this paper will be very important because by use it, we can do some comparison between band gap and between direct and indirect band gap. That will be, I think, clear to us. Here, like we say, we have to curve conduction energy band here, and the bottom point at the conduction energy band here, this point, and sorry, valence energy band here, and the upper point at the valence energy band here. At the same time, here we see the energy emitted from the valence energy band go to the conduction band. And we have two different lines. Here, generation of an electron hole pair, this energy. And at the same time, we can see the difference between the indirect band gap here and with the first diagram. Here, the point, the bottom point at the conduction energy band under another point in the K line. Note the same situation with the direct band gap. But we have another important thing we must note. It's here in the direct band gap, we don't have any change of momentum. But in indirect band gap, we have change definitely. We have change of momentum. If we have indirect band gap, that's mean we have change of momentum. That's it. And here, and the direct band gap, the electrons can through directly from valence band from here, from valence band to the conduction band. Like this line can through directly, easily from the valence band to conduction band. But the situation is different with the indirect band gap. Why? The electrons can through from the valence band to conduction band, but under one condition, definitely under one condition. Without this condition, no way the electrons can't go from the valence band to the conduction band, no way. What the condition? The condition is here the electrons need additional momentum. Without additional momentum, no way. The electrons can't escape from the valence band. That means we need additional momentum term to come through from valence band to conduction band. Now let's talk about what the result, what the equation, general equation to the energy. Like we say, energy equal HV. To prove this equation, this is the last line, the last result, I will use this math track by put dot 2 pi divided on 2 pi. We know the last result to this side will equal 1. But take a look what I will say, what I will do. Here, the result, the equation will be h divided on 2 pi dot 2 pi dot v. Now, like we know, h divided on 2 pi equal h bar, because that we can write here h bar. After that, 2 pi v, this equal w. That means the last equation here to the energy will be h bar w. Now, let's know what the last equation, the last result of momentum. Momentum, like we know, P equal h divided on lambda, the wave, dot 2 pi divided on 2 pi. I will say the same trick. And we know 2 pi divided on 2 pi equal 1. That's mean the sphere in the math equation. H divided on 2 pi dot 2 pi divided on lambda. Here, when h bar divided on 2 pi equal h bar, at the same time, 2 pi divided on lambda equal absolute value equal k. That's mean here the momentum equal h bar dot absolute value here, the k. This will be important because I will use it at the energy to find the result of kinetic energy. Now, to find the result of kinetic energy of a free electron, like we know, the kinetic energy of a free electron equal minus m dot v square. V the velocity, like we know, m the mass of the electron. By use another method trick to make the results be easier to us, I will put dot m divided on m, and the last result will be 1. That's fair in the math equation, in any math equation. That's mean the equation will be mv between two brackets square divided on 2m. But here, let's write and note this important thing: P equal mv. That's mean the kinetic energy will equal the momentum square divided on 2m. And at the same time, P equal h bar k, here like this equation. That's mean E equal h bar k between two brackets to force 2 divided on 2m. Now, indirect energy band semiconductors, I selected this diagram because I was thinking this diagram is be easier to us to understand the important information. Like we see here, the important thing, and I used the red pencil, absorption, photon absorption, and emission photon. Here are the absorption line. Here, this is the shorter line. The absorption here equal energy band gap minus EP, energy of momentum. And the longer line here show to us the emission photon. The difference will be plus energy band gap plus energy of momentum. Here plus at emission, at absorption we'll put minus. This will be important here. Now let's talk what the difference between photon and phonon. Photon and phonon. Photon is a quantum of light, but the phonon is a quantum of lattice vibration. Lattice vibration. Maybe the pronunciation to all of these words be maybe similar, but big difference between them. Now let's talk about the energy conservation. After we know what the difference between photon and phonon, and what the difference between indirect band gap and direct. Now let's talk about the energy conservation, E photon. Like we said before, I said before, E photon equal at emission will be here put plus energy band gap plus E of photon. At the same time, to the absorption, we'll put minus E photon equal conduction band minus E of photon at the absorption. Now let's find the momentum, the result of momentum. Momentum P photon equal PC, that's mean at the conduction band, minus PV, that's mean at the valence band, minus P photon, the momentum of photon. And all of these are calculated by using the same unit, kilogram dot mass divided on second. All this, the last information, I take it from the photovoltaic to Stephen Cole. At the end, I want to dedicate my video to my wife, and that's it. Kendinize bakın. Gelecek derste görüşürüz. Thank you about your attention. Have a good day.